I'm going to present a paper named YuZu, dealing with volumetric video streaming. This is a paper objective to NSDI 22. So this is a sample GIFs of the point cloud and volumetric content. So the motivation of this paper is to improve the quality of experience of volumetric video streaming through employing the 3D super resolution. So there are some related works such as volumetric video streaming and point cloud super resolution, and visual quality assessment of point clouds, and 2D video streaming systems that utilizing super resolution. Okay. So for the motivational study, they naively apply the 3D super resolution technique to the volumetric video. So they upsample every point cloud frame from the 2-minute video with 30 FPS, which consists of 36 22 frames. So for each frame, it has 100K points, and the total data size, the video size, is 1.4 gigabytes. And by utilizing the 4x super resolution, it reduces the bandwidth by 74%. So it means to use 4x super resolution, so they only need the 1/4 of the point. So it reduces the total video size into 0.36 gigabytes. And they train the 4x SR model, which is less than 1 megabyte. So it reduces almost 75% of the total data size. And so after the super resolution, after the upsample, you may want to know whether the result is visible and satisfiable. So to check that, we usually use the EMD, Earth Movers Distance, which was introduced in the Williams presentation previously, I guess. By matching the points of the upsampled point cloud and the ground truth point cloud, and calculate the distances of each point matches, that reduces the total sum of the length distances. So it's less than 1.47 centimeters, which is quite good. However, as you can see from this, or you may have inferred from this motivational study, there are several challenges that we need to solve if you want to build a system that utilizes 3D SI. First of all, so EMD is not an actually good metric for quality of experience. So they do not consider the quality of how they represent, or the colors, even they do not consider the colors of the points. So there is a lack of quality of experience model. And I have not mentioned, but the inference time of the live PU GAN is 0.1 FPS. So it is 0.1 FPS, which is highly unacceptably poor considering the runtime inference. And also, the SOTA models usually do not consider the color of the point cloud. Yeah.
So what is the full name of EMD?
EMD is Earth Movers Distance. Earth Movers Distance. And so the key approach is the authors propose is like this. So they build and tune the SRQOE model, and they train and optimize the 3D SR process. And they cache and reuse SR results, and adapt the network and compute resource, and follow the SR out. So let's start with the first QoE model. So they empirically define this QoE model, like this equation. And let's explain one by one. So capital QI is the quality of the I frame. And each frame I has lots of patches, which is denoted with the J. So the lowercase qij is the quality of the J's patch of the I frame. And Vij is the visibility of the patch, J's patch, which is determined by the user's site and the point cloud position. So it's basically the QI, the quality of the iframe is basically the average of the quality of each patches, every patch, and the quality of J's patch of the ice frame is defined in this way. And there is G and H functions. It is defined in this way. So they have some variables here, such as Dij is the density of the point cloud, Rij is the super resolution ratio of that patch, and delta ij is the distance from the user site to the point cloud object. So it's basically just multiplication between these variables, and they use the weighted parameter. They have the weighted parameter for each functions for the delta. And EMD is used, and the EMD here is the distance, the earth mover's distance between the upsampled point cloud and the ground truth point cloud. So G is for the positive points, positive score of the quality of the J's patch, and H is the negative side of the J's patch. So if your upsampled point cloud is quite far from the original one, then you get a negative quality. And they determine this in an empirical manner. And then there is some other variables like I-patch, I-frame. I-patch is the standard deviation between the patches in the I-frame. So you can get the quality variance with this. You can consider the quality variance of the patches in the I-frame. And I-frame, this one is just the difference between the quality of previous frame. And store here is just considering that this is for the transmission task. So if there occurs a store, then you get the negative quality of experience.
Indication, even if EMD is really low and EMD is really high, but the density is much higher than that, then you can get high QE.
Theoretically, that makes sense. However, like density here is defined in 1/4 or like 1/2 or 3/4. So there is not much room to dramatically increase the density. Okay, so this is how they build their QA model. And then there are like several weights you can see. So UP, UF, US, and also the W1 and W2 are parameters you need to tune. So they did the user studies to get those values. They did two very huge user studies. First one is to check whether they actually get the QoE gain from the super resolution. So they made 8 combinations of possible strategies, like using the 1/4 and upsample it with the 1 times, 2 times, 3 times, 4 times, and using only 1/2 of the point cloud and using the upsample with 1 times or 2 times, like such strategies. And there are 8 strategies, and we need to compare 2 pairs. So there are 28 combinations. So for 28 combinations, they also consider the distance from the point cloud, and there is 112 cases for each user to report their experience. So for each pair, they could rate it whether the left and right videos, which one is better and how. So the right one is much better, like a little better, like in this, like seven scales. And after that, so there is a figure later that shows how much the super resolution of sampling was effective for the QoE. And there is another user study for the impact of the parameters. So they need to determine the parameter weight here. So there are like lots of parameters such as, so they accept the ground truth strategy here using the whole sum point cloud. So there are only 7 strategies, and there are still like 4 distances, 1 meter away, 2 meter away to 4 meter away. And there are some other variables such as interpatch variance, interframe differences, and also store variables, store such as like 0.0 store or 1% store or 3% stores occur. So there are actually like when you multiply these numbers, you get the 756 combinations, and from those combinations comparing, so 756 choose 2 is quite a lot of big numbers, so they just show 100 randomly selected video pairs, and then they compare 2 video clips and rate them. And they also did use the AMT for the survey. And after they get the results from these studies, they tune the QoL model. So after they get the ratings, they need to change it into numerical values. And they made a kind of graph, directed graph, and they use PageRank to make it into numerical values. And they cross-validated the result, also check the cross-video prediction correlations. And as a result, they get the model that they can infer the user quality for the 80% of the cases with less than 20% error. And after that, they will use this QoL model later. And they did some like trim and optimization process for the 3SR inferences. First one is kind of a clever trick that can be applied to the point cloud case. So when we think of like 4x, when we think of using the 4x super resolution, we usually think that using the input. So for the 25K points, we usually do the 4x super resolution. However, like they found out that they can just do the 3x super resolution, and they get the 75K, and they can merge the input point cloud with the 75 output point cloud, and then they can make 100K. So in that way, they can reduce the 4x to 3x or like 3x to 2x, which is kind of simpler and arbitrary. And also they profiled the whole process of the PUGAN, and they found out that the feature extraction phase is quite heavy and takes a lot of workload. So they used the SORA model of SKF, which is the spherical convolutional funnel. And actually, they did not explain the rationale behind why this color makes the process much faster. But anyway, they showed the result that this was more appropriate for their task, and also it was effective to use this spherical funnel to accelerate the inference. And then they also used the simple cubic cell-based approach to generate the patches. So in the previous models such as PUGAN and NPU, they used the PointNet based kind of patch generation, which was PointNet was related to convolution funnel. So for the patch generation, they usually do the downsampling for the point cloud to get the C's, and then they do the K nearest neighbor to make the patches. And after that, they do super resolution. However, when they upsample the seed and patches, they get the redundant points in other patches. So they need to remove those duplicated points in other patches. So they have to also execute a further point remover process, which is post-processing. However, by using the simple cubic cell-based approach, they can accelerate the process by not doing the KNN and downsampling, and also they do not have to do the post-processing. Okay. And then they cache and reuse the SR results. So to cache and reuse the results, you need to determine whether two patches are similar or not. So to do that, first they match the points in patches. For two patches, they calculate the minimum weight matching, which is conceptually, I guess, quite similar to EMD, but the purpose of the EMD is to get the average distance between the point pairs. However, in this case, the output is the matching of the points. So after they get the match from the end-over-end process, they determine to determine this similarity, they define the PMV, point motion vector, which is the kind of the pair. So by the two pairs of points, you can make a vector, and they call it a PMV. So, so the patches are, so they define that the patches are similar if all three conditions are satisfied. And these are the conditions. So the numbers of points in two patches is differ less than eta n. Also, the average PME, so the distances between the points pairs, average PME length is less than eta a. And the top 90 percentile shortest PME, so the top 90% shortest points transformation or move distance is less than eta b. In these three conditions are satisfied, they say that the two patches are similar. And they showed with this experiment that by relaxing the condition of the eta a in the x-axis, they can get the trade-off, they can observe the trade-off between the accuracy and reuse ratio. So the EMD here is the kind of the accuracy, and we can think that when EMD is low, the accuracy is good. When it is high, then the accuracy is bad. So as the eta a goes up, the accuracy goes down, and you can make use of more reuse ratio. Yeah, so yeah, you can use the super resolution a lot more with the lenient eta a. Relaxed condition. And yeah, there might be quite a lot of contents to explain anyway. So, and also they need some kind of network and compute resource. They try to deal with them. And to understand this part, you need to know some concepts or words. So video is divided into segmented into n chunks, and consists of f frames, which are segmented into d blocks, and each block has multiple patches. And they try to determine, seeing the next double chunks to determine the download size of the current chunk, and also determine the super resolution ratio of each D blocks. And so the problem formulation is like, for next double chunks, they are trying to determine the strategies for double chunks and B blocks. So, and there are 8 strategies, so 8 to the double B. Yeah, there are that much problem space. So they determine one of the combinations of strategies from there. And there are some other possible approaches, such as memorization using fast MPC. But that is not practical because their problem space is quite large. And they could use other approaches such as PANSI, but they just briefly mentioned that it may occur some inference overhead, and they also cite some kind of recent NSDI work that RL might not be good as just using simple buffer or something. And yeah, they propose a lightweight 2-stage decision The basic idea is to divide the whole this network and compute resource trade-off situation into two stages, and they first do it in the coarse-grained way, and then they do it again in the fine-grained way. So before download, they decide the quality and the SR ratios of chunks coarsely, and they do not consider the blocks here. So that's why it's kind of coarse. And by doing so, they can reduce the problem size, and they can determine the parameters for the chunks to download and do SR. And then they, before the upsampling, they decide the SR ratios again using more sophisticated way, simulated image. And they consider only one chunk here, so they determine for each blocks using this approach. And they color the super resolution output. Basically, this is kind of simple way, and they approximate the upsampled point color based on the input point cloud with the nearest point distance, And to speed up, they did some kind of technique, which were in the appendix. So they do the nearest point search on up3 as they import it, and they cache and reuse the result of search point. And now the evaluation. So they show the 4 types of videos, and they use 2 QoE measures, and they tested on various network conditions. And they did on the high-end PC and also Jetson mobile, kind of representing the mobile device. And so I wrote down some kind of takeaway from the evaluations and selected some of them. So from this one is the figures from the user study. And what you can take from here is that SR does increase the QoE. So as you can from the left figure, there is 1x1 and 1x2, which uses only 1/4 of the point cloud and it applies the 1x super resolution and 2x super resolution, 3 to 4. So by using the higher super resolution ratio, you can see the QoE actually goes up. And also another takeaway here is the size and SR ratio choice is better. So when you use this higher super resolution ratio, you can get the higher QoE score. However, you need to use more compute resource. Compute resource. And also, quite obviously, when you use the ground truth, the 4x1 case, you get the most highest QoE. However, you need a big bandwidth to support it. So there is some kind of trade-off, or the choices can be different according to the condition you need to decide the exact condition. And the third one is so this one, the left one is the QoE when the distance between the object point cloud content and the user was 1 meter, and when it goes to 4 meter, actually they go all similar. So when the object is quite far from you, you may not need to upsample hardly. You may not need to. You can just use the smaller point cloud with low ratio of upsample. And for this one, so the left one is kind of subjective quality metrics, and the right one is quite objective polymetry, which is PSNR, that's committed to all of that. So the left figure on the right pair is YuZu, and right one is the PUGAN, which is live one. And even though they did a lot of optimization on the YuZu, they still get the quite comparable QoE. I mean, like the PSNR compared to the PUGAN, live version of the PUGAN. So they gets lots of memory advantages and also latency advantages with the optimized version, but they get good PSNR. And especially when they are the 1x4D, it's using the caching and we're using the super resolution review. Though they get a good PSNR. And they also did some performance breakdown to see the to conduct a relation study and see the effect of these components. Yeah. So, and the takeaway from here is M4 is where you add the SKF instead of the PLNet based convolution. And M5 is the merging tree, and the M6 is the using caching. So SKF significantly reduces the memory usage, as you can see in the left figure, and improves the latency and improves the FPS a lot. And merging tree also quite effective, and caching boosts the FPS performance a lot. And they also tested their system in diverse network conditions. So there are also some takeaways. So 4x1, which using the original point cloud, the ground truth. Using the 4x1 leads to store and drops the QoE, especially in lower bandwidth. So when you see the 50 megabps in that figure, they actually goes down and they show the negative QoE. And also some options like 4x1D, which uses caching with the ground truth, caching with the original point cloud. They shows good QoE. However, when the bandwidth goes lower, their QoE drops a lot. And the full version, which is the YuZu, it achieves the highest other than ground truth for the QoE in the case of 75 megabps. And here is the dynamics. So this is the stable condition, stable network condition, and this is the dynamic network condition. The takeaway here is that so this way it goes better, and there is a YuZu. It achieves the normalized QoE, which is quite high, while balancing the data use with the almost half of the data are used. So yeah, that was for the paper and for the critique. I think yeah, the strengths are it was quite a thorough research, consisting from a type motivation study and two huge user studies and also a large system building. And they evaluated in various conditions, including micro benchmark and large LT network. I did not mention during the presentation. And they attached a big, like several pages of appendix also. And for the weaknesses, I have much to talk about as a weaknesses. So I picked some kind of minor issues. They kind of borrowed the SKF component from other SODA papers. So understanding of the performance improvement is not clear, I guess. The reasoning behind that is not clear. And also the effects of the components. I think using the cubic cell patch generation, and SKF together have some effects on both sides, but those are not mentioned and discussed inside of it. Yeah, that was it for the presentation. If you have any questions, you may ask.